In this part of the video, we are going to discuss power in the AC circuit. So I would like to once again welcome to you, welcome you to this YouTube channel, Tech Guru Gautam Prasad, and let's discuss power in the AC circuits now. So here, uh, with the help of this profile of current and voltage, we can discuss the power in a better manner. So as you can see here, sorry, this is the blue color. With the help of blue color profile, this voltage profile has been shown, and this red color is showing you the profile of current. And as the voltage and current together decides the power in the circuit, this power is negative here. As you can see, the current is negative in uh, this region. So, a positive voltage and negative current is ultimately leading to negative power. So, up to maybe this place, up to 90 degree, you can see it is in the negative zone. And ahead of 90 degree, now it is in the positive zone. So, during one half cycle of the half cycle of this sine wave, you can see this power is having two one full cycle, two crests, one negative crest and the other is positive crest in the case of power. So half cycle of the voltage creates two full cycle of one full cycle of the power. Similarly, we can see in one full cycle of AC voltage, we have got two complete cycles of power. So this is positive side, this is negative side, positive side. So you can clearly say that power is pulsating in nature. Once it is going negative, on the other side it is going positive. So that's it. Electrical power is the rate at which the energy is being consumed in the circuit, and as such, all the electrical and the electronic components and the devices have limits to the amount of the power that they can safely handle. This is very important. For example, a quarter watt resistor or a 20-watt amplifier. These are the examples. So, electrical power can vary, can be time varying. This is very important. Electrical power in the case of AC is time varying, it is varying with the time. Either as the DC quantity or as an AC quantity. The power in the circuit at the instant of the time is called instantaneous power. So, at a particular moment, if you will consider the amount of the power, this is called instantaneous power. So, instantaneous power is uh, given by the multiplication of voltage and the current, as you can see here in the case of AC, also the power factor, as we had discussed earlier. So 1 watt, which is the rate of the expending energy at 1 joule per second, will be equal to the volt ampere product of the volt times 1 ampere. And then the power absorbed or the supplied by the circuit element is the product of the voltage and the current. So if we had DC circuit with a resistor R ohms, the power dissipated by the resistor will be like this: B equal to V into I, V square by R, because I equal to V by R. So that value has been substituted here. Or it can also be represented as I square R watts. So where V is the DC voltage, I is the DC current, and R is the value of the resistance in the DC circuit. So the power within the electrical circuit is only when both the voltage and current are present. So these two components have to be present in the circuit, then only the circuit will have power in the picture. That is, if the circuit is open or it is not closed, then we cannot have power. So here DC resistive circuit has been shown. There is a resistance of 6 ohms and 12 volts of DC power supply source has been connected across this resistance. Now it is causing the current of 2 amperes. How? P is equal to power is equal to volt into current. So 12 into 2 is 24 watt of the power. P is also V square by R, 12 square by 6. Again it is 24. P is equal to I square R, 2 square, 2 is the current, 2 ampere, 2 square into 6 is 24. So with the help of all these three formula, you are getting the same result. So you use either of the formula of the three, either of the three, you will be getting the same result. Now let's discuss electrical power in AC circuits. Okay, so as we were discussing here, the sinusoidal voltage is like this. V instantaneous value of the voltage is given by V max sine theta. So the theta is varying on the x-axis. You can see the theta is varying. So basically, when an alternator rotates to create this voltage, it has to, it keeps rotating. So at various angles, it is giving the, the level of the voltage that has been shown sinusoidally. As the instantaneous power, if we talk about at any instant, the amount of the power, then P is equal to V into I. Now V instantaneous is Vm sin omega t plus theta V. I is equal to Im sin omega t plus theta I. So you uh, if you want to calculate power, you will have to multiply these two instantaneous values. So if you multiply this Vm sin theta omega t plus V theta V multiplied by Im sin omega t plus theta I, P is equal to Vm Im sin omega t plus theta V and sin omega t plus theta I. Now applying the trigonometrical product, this is a formula sin A into sin B this is a formula. Okay, you have to take it as a formula. Sin A into sin B is equal to half of the cos A minus B minus cos A plus B. Now there is no proof here. We can discuss. So you take it as a formula. So based on this, you can further calculate from this one. So sine half of the sine half of the cos A minus B minus cos A plus B. Okay, so P is equal to Vm Im by 2 divided by 2. So cos theta, based on this, cos theta minus cos 2 omega into omega 2 omega t plus theta. So you have to use this formula sine A into sine B. Here sine A, value of A is omega t plus theta B and B is sine B. So value of B is omega t plus theta I. Right. So if you do A minus B, then it leaves you theta B minus theta I, or that is theta, only theta, and cos 2 omega t plus theta. So this is what we get as a result, and Vm Im by 2 can be written as Vm by root 2 and Im by root 2. So this becomes Vrms into Irms. So as a result, you see the power is the value of RMS value of voltage and RMS value of the current and this component. Okay, so where V and I are the root mean square value of the sinusoidal waveform, are represented by a small v and a small I respectively, and theta is the phase difference between the two waveforms. Therefore, therefore, we can express the instantaneous power being P equal to Vi cos theta minus Vi cos 2 omega t plus theta. And this equation shows that the AC power has two different parts, and therefore the sum of these two parts. The second term, especially the second part is varying sinusoidally whose frequency is equal to twice the angular frequency of the supply due to 2 omega part. Okay, so in the case 2 omega part, this thing 2 omega we had seen it was having the frequency of 2 omega as in the half cycle it was completing one full cycle, and in one full cycle of the voltage it was completing two cycles, so the frequency was doubling. That is why it justifies the 2 omega t at that place that we were discussing just now. So this 2 omega, this second term terminology, 2 omega t part is justified here. Okay. The first term, however, is constant and whose value depends on the phase difference theta between voltage and current. As the instantaneous power is constantly changing with the profile or the sinusoidal over time, it makes it difficult to measure, and it is therefore more convenient and easier on the math sheet to use average or the mean value of the power. So, over the fixed number of the cycles, the number or the value of the instantaneous power is given by V into I cos theta. And this becomes the formula for the power in the AC circuit. So, where theta is the phase difference between the voltage and the current, that's quite obvious. And VRMS and IRMS are the instantaneous values of the voltage and current. Here Z is equal to, as we have seen in the RLC circuit, that Z, that is impedance, equal to square root of R square plus XL minus XC to the whole square. And this is theta is cos inverse of R by Z, sine inverse or sine inverse of, I don't know, theta is missing here, so there is some mistake here. So P becomes V square by Z cos theta, and P is equal to I square Z cos theta. So that is what the power is. And AC power example number one. This is a basically numerical. So the voltage and the current value of 50 Hz sinusoidal supply are given as V equal to, that is instantaneous value, 240 sin omega t plus 60 degree volts, and IT equal to 5 sin omega t minus 10 degree amperes respectively. Find the value of the instantaneous power and the average power absorbed by the circuit. So you have to go in the same way as you uh, proceed earlier. So P equal to V into I, these two instantaneous values have to be multiplied, and after multiplying you get this thing, 240 sine omega t plus 60 degree sine omega t minus 10 degree, and you have to calculate it based on sin A into B formula that we discussed just now. So it becomes 240 into 5, uh, and substituting these values you get 1200 sine this value. And if you proceed, keep on proceeding, breaking it on this formula, this becomes Vm to Im by 2, and you get ultimately average value of the power, Vm into Im by 2 cos theta V minus theta I, and that becomes 60 degree minus of 10 degree, that means plus 70 degree cos So 600 into cos, this comes to be 205.2 watts. So this is the average value of the power. You may have noticed that the average value of the power is 205.2 watt and is also the first term of the instantaneous power, as the first term was constant, and it is the average and the mean energy changes between the source and the load. That's it. AC power is in the purely resistive circuit. Now let's discuss. So in the purely resistive circuit, what happens? The voltage and the current remain in phase. There is no phase difference between the phase angle is zero. You can say. So they are in uh, phase. So vectorially, if you want to show, these two vectors have been shown here. This red color is the I vector, and blue color is V vector, and this is the anticlockwise is the direction of rotation of these two vectors. Here V is the voltage across the resistor, and IT is the instantaneous current, which is equal to VT, that is instantaneous voltage divided by R, that has been brought from the Ohm's law, and Z equal to R because it is resistive. The total value of the impedance is equal to the value of the resistance itself. So P is equal to V into I cos theta, as from the earlier discussion. Cos is 0 degree, so it is 1. P is equal to V into I, that means V into I watts. So in the resistive circuit, you have the maximum power. So AC power waveform in the pure resistive circuit, if we see, look at this. This is very interesting. You have positive voltage, you have positive current, so you have positive power. And also you have negative current, you have negative voltage. So the multiplication of negative into negative is positive. Again, you have positive power. So in the case of resistive circuit, you are saying the uh, power is not going in the negative side. The power is always positive. So this is very interesting to understand and know. In the resistive circuit, the power is positive always because they are in sync. It goes to negative only when there is a phase difference. For the negative current, power also goes to the negative side, as we had seen earlier. So AC power in purely inductive circuit. How will be this behavior? So here is the uh, purely inductive circuit, and this is the phasor diagram. Your voltage, your current is lagging by 90 degree. Theta is 90 degree here. So the waveform is shown like this. The current is lagging. Current is starting from the negative side, while the voltage is for zero, it is negative. So it is lagging. Your current is lagging. So the power will go negative here. So if you want to see it in the waveform of the waveform, you can see it here, that for the negative current side, it is going to negative side and then again positive. So in one cycle of the voltage, it is completing two cycles. The power is completing two cycles in one cycle of the voltage. So that is it. The frequency of the power is double of the frequency of the voltage or the current. So now let's see it in the case of purely capacitive circuit. This is your purely capacitive circuit, X equal to 1 upon 2 pi Fc, and IT instantaneous current is equal to VT instantaneous voltage divided by XC, the capacitive reactance. Resistance, uh, uh, we must mention here, is 0, as we have taken purely capacitive circuit. Purely capacitive circuit does not contain any resistance. Okay, but here current is leading. This is your voltage vector, this is your current vector, and this theta is 90 degree, and this omega is showing you the anticlockwise direction of rotation of these two vectors. So z angle minus 90 degree, 0 minus j1, right? And here this is red color is showing you the current profile. This blue color is showing you the profile of the voltage, and these two waveforms are showing you the instantaneous values. Here also you can see that the voltage is positive, the current is positive, so this half cycle of the power is positive. On the other side, as the current is going on the negative side, here this power is negative here. So again, the cycle, this for the one cycle of the voltage, this power is completing again twice the frequency. All right. So this is how it goes like. So this profile gives you a better picture of the power. Power is also pulsating in the case of purely inductive or purely capacitive circuit, unlike in the resistive circuit where the power is positive always. So that is the difference. We will discuss up to this point in this video. Now we will stop, and rest of the thing we will discuss in the subsequent videos. Thank you very much for staying with me. Stay tuned. Don't forget to subscribe, like, and comment. Your comments are most welcome, as it gives me ideas how I can make my videos better, simpler, and easy to understand. Thank you so much. Stay tuned.